Like Susie said, I'll be talking about 3 steps towards data labeling excellence. I'll first go into a short agenda and then introduce myself here. Basically, what are we going to be talking about today? We're going to be talking about unstructured data and labeling it. So hopefully you are all excited about that. We're going to be talking about why curating labeling errors matters, why you should track them, what makes data labeling much harder than it might initially seem. I'll present 3 lines of defense that you can employ through the Kili platform, of course, on data quality in labeling projects, and then I'll wrap up with some key takeaways. So like Susie said, I am Michael Van Moyer. I am a senior solutions engineer at Kili Technology. Kili is a data labeling platform that allows you to transform your unstructured data into high quality training data and deliver successful AI. Kili has built a platform that allows ML engineers, business stakeholders, labelers, and team members build and curate high quality data sets from unstructured data at scale. We work with the companies you see there below on the screen, as well as many others. We're headquartered both in New York City and Paris, France. So let's talk about why curating labeling errors matters to producing high quality data sets. We see from the stats shown that there are errors in data sets, both in public and private data sets. So during the NeurIPS data-centric AI workshop, facilitators stated that 3.4% of labels in popular ML test sets were erroneous. So that's not zero, of course, and it's an underlying thing. So they are known errors, and they aren't being done anything about. So QuickDraw was one of these ML test sets, had about 10% error rates. And really the percent stated were a lower bound, as they only really tested a subset of the data set rather than the whole data set. The widely used ImageNet data set, of course, contains 6% errors, again, not zero. And Lyft even stated that 70% of scenes labeled by an outsourced labeling service provider were missing at least one object. That has potentially deadly consequences if used to train a self-driving car model, for instance. You cannot outsource quality, you must engineer it from the beginning. So now on to the business impact of data quality, which I alluded to slightly in my previous slide. These figures come from Facebook. So a 10% decrease in the accuracy of labels means a 2 to 5% decrease in the performance of the model, so the actual accuracy of the model and prediction. It also means that if you have those errors, you would have to double the data set size if you want to keep the same model performance, which means that you have to label twice as many things, which is doubling your budget for labeling. Now, when you consider that data labeling is one of the main costs of ML projects, this means that the cost is significant. So what I'm telling you is that data quality is worth the investment. Okay, so why is this so hard? And what makes it really hard to do? Well, even the most simple yes/no labeling tasks can be really complex. Take this labeling job here to illustrate the current challenges in just a simple task. So the naming and the position and size of the bounding box. So, what is going on here? We're labeling with a bounding box. We see a windsurfer, and the task at hand here is to label the windsurfer. Okay, what does that mean? Does it mean the actual person? Does it mean the entire apparatus? Is there's some inconsistency in this labeling here? So even the most simple projects can be ambiguous. So you have to provide good instructions at the outset of your projects to get performant labels. So here's another example illustrating how even great labels can't guarantee space coverage that the data diversity actually matters too. So we can see on the left that there is a certain bread class. They all seem relatively similar. It's some type of whole wheat homemade bread. We can label all of these and classify them as bread. But then what happens when we encountered sliced white bread or bread with butter on it? A machine learning model trained on only class examples on the left would not do a very good job at predicting that this is bread on the right. So you come across a lot of edge cases, and you have to understand what you should actually do with them. It really depends on the task context. All right, so enough introduction. I'm sure you all agree that label quality actually matters. It's hugely important to the performance of models, and that it might not be as easy as it might seem from the outside. So I'm going to move on to the meat of my presentation, Kili's 3 lines of defense to ensure data quality for labeling projects. And it really, again, it's 3 lines of defense: project design, the labeling team, and the QA processes. So for project design, you have to design and engineer an ontology or way of labeling, as well as the data sourcing first, to provide clarity on what's right or correct for the actual labelers to actually perform that work. So you have to design it right first, and then you have to train a team. So training a labeling team to catch errors early through dynamic collaboration and feedback to get things right on the first try, or maybe the first or second try. And then if that doesn't work and you're still getting a lot of errors, then you have to implement, of course, QA processes to catch everything else. So it's really trying to identify patterns and gaps in what you didn't realize you should have done at the outset. So you're trying to capture 80% of everything correct, in the first 2 steps, and then whatever remains left is, oh, we didn't catch this. We weren't smart enough to actually understand everything at the outset. So implementing those QA processes to identify patterns and gaps in the remaining errors. And then it's an iterative process. So you iterate around this cycle to constantly improve your both project design, how you train people, and of course your QA processes. So diving a bit deeper into project design. So, really developing first an agile approach, starting small and iterating fast on an ontology and guidelines. Maybe this is a single machine learning engineer that is working in a small data set that's a subset of a larger data set to really understand, okay, what are my labelers going to run into? And you'd have maybe your first batch of data labeled by a machine learning team. And then you may test that out with a small labeling team to get a feel for, okay, what are they going to run into? And then again, you iterate around. From that, machine learning engineers can either provide input to a team manager or someone who understands kind of the use case to develop some labeling guidelines, define each class, understand the business use, add specific labeling instructions, and add in a section on edge cases, how to handle them, what you should do, and then regularly update those guidelines during the project, of course, because you're iterating around trying to improve how you're doing and approaching this labeling task. And then moving on to the ontology, defining that it's going to provide sufficient information for the model so they can actually predict things. But then you also want to make sure that you're labeling the right things so that you get the business value at the end of the day. So you need to design it to be usable for both your labeling team, easily separable classes, clear names, right language, etc. And then understanding the trade-offs between the model objective and the labeling capabilities. So it's not all black and white. There's many, many shades of gray, a lot of disagreement around what is truly correct, because in unstructured data, it is a perception thing. It is a human activity, this labeling, and there will be disagreement. So I'll step over to a small case study here on how you might approach building an ontology for a damage detection use case. So a structured response offers the labeler guidance on kind of what's possible, what classes there might be. While this doesn't mean that classes aren't in the response won't show up, it flags the labeler to ask a question. So an alternative to this is to add an unsure unknown class. Free response can be helpful in some cases, but generally invites additional complications in the post-processing and modeling steps. There's misspellings, there's misunderstandings, there's preconceived notions about the data set and what classes might be present that can hamper project progress and quality. However, when they're in cases where there's like transcription of words, possibly with like optical character recognition in the background, then free response can be really useful because if the task is articulated well, you can actually have your labelers correct errors in that OCR model. So then understanding the trade-off between concise classes versus exhaustive classes. Exhaustive lists can make labeling way harder because it can really overwhelm labelers searching through a big list of things for the most appropriate class. Concise classes are not only easier to build models off of because there's less total data required to understand, okay, this is a separable class from a different one. They're also way faster to label because it gives less room for error. The trade-off, of course, is that concise classes may not be as detailed as you might need. Yes, there's a concise class. All right, and then finally, data issue flags can be useful when the quality of the raw data is unknown. It gives an opportunity for labelers to quickly recognize and categorize each such data as having an issue and move on to the next asset. Reviewers can then quickly filter and sort through these issue classes to help diagnose the issue, or they can help inform the model as to more nuance around the data. And then there's, of course, assumptive versus evidence-based classes, e.g. A riot versus protest, or is it just a group of people capturing emotion or intent? Assumptive classes typically require a lot more labelers to be confident in the consensus for what the class truly is. And of course, it invites a bunch of bias as well. And then the final trade-off I'll talk about is qualitative versus quantitative. So a few flavors of that: amount / extent of damage, low, medium, high, or totaled, versus dollar amount of damage, which might require a subject matter expert or potentially multiple opinions and maybe a geographic component for where this work might be done. And then another example is good or bad. Again, assessing intent or character introduces personal bias. Of course, a great example of this is if you have a cancerous cell and you're labeling it as bad, that's not really helpful. We all know that cancer is generally bad, but perhaps a percent of a scan or a size of a tumor might be more useful in that case. Okay, so going along this theme of damage detection use case, we can understand why this might be a bit nuanced. So in this example, is the damage on the rear, the side, or the bottom? Well, it appears to be on the rear, but it's also in a rear corner. So does that fall into the rear or the side? And it's also near the bottom. It's not exactly clear. A more specific ontology might be more helpful here for rear passenger side. And then again, here's another example. The damage is on the top of the car, but it's also on the hood of the car. The top of the car might be perceived as the roof of the car versus the hood of the car, although it is all on the top plane of the car. Again, I might be sounding like I'm semantically being silly here, but it does matter. And then this one is pretty straightforward. The damage is on the side of the car. It's on the driver's side door. But a complicating factor and what you see in real world data is that there's another car in this picture that does not appear damaged from what you can see of it. So anticipating how complex the task and the data is paramount to designing a good ontology, but you don't have to get it right on the first try. You are allowed to fail fast and iterate. So as I was thinking through all of these slides, you kind of saw my thought process of, oh, it could be better if I did this. And that's exactly what you want to be talking about with your team in understanding how to build these ontology. Okay, second line of defense, the labeling team. So there are three pillars to this: how you're staffing your project, how you're training those people staffing the project, and how the interface that you're using can introduce safeguards against doing things that aren't correct. So for staffing, there's of course the trade-off of insourcing versus outsourcing. There's cost for insourcing and outsourcing. People's time, they might not always be labeling. They might have other parts of their job that they're doing if you're insourcing. If you're outsourcing, that might be a very specialized service. They may have domain-specific knowledge inside the organization versus outside. Again, it will depend on the context of the labeling project. And then how you actually assign things to the people staffing it. So it can depend on expertise. It can depend on the actual task at hand. Maybe some people are better at one thing versus another, or I've only been trained in one area or another, which gets onto continuous training. So, really quality is a dialogue. It is a collaborative effort. It is based on feedback and direct training for the people actually doing the work. And you might also want to introduce the concept of benchmarking, benchmark project for new team members, making sure that they are actually able to do what you train them to do before you release them and have them label new data that no one has seen before. So you can be confident that they'll label it correctly. And then interface safeguards, providing information on the context when labeling, and I'll have a couple examples after this that will illustrate that. And then building in safeguards in the interface to limit errors generated by the labelers. So that can be field formatting for documents, the UX of buttons, et cetera, et cetera. So I have a couple of GIFs here to show some direct collaboration and some synthesis of data to have administrators actually quickly react to what is going on in the project. So you can see here, I have someone giving some feedback. This is a labeler saying, I'm not sure how to label this, and they are able to directly communicate with a team manager that can then come and look and say, hey, there's an open question. I can actually open that up and see that, and then give the feedback back to the labeler saying, oh, this is how you do this, or, oh, we need to think about this at a higher level before we can proceed. And then again, having direct access to instructions, very important. So of course you will want to write instructions for any labeling project and then have them easily accessible to the labeling team. And then providing tooltips in the ontology metadata to say, okay, this is exactly what I mean by is this relevant? Is this for what position? Having those tooltips can be very helpful for understanding the task at hand. And then, of course, there's direct field validation or forcing certain types of entries in certain places. Here I have several examples. One is a date field. It will only accept dates. One will accept anything. That's the middle one that doesn't get anything written in it. And then the bottom one there, it will only accept numeric input. So again, it's preventing preventing errors before they happen. Okay, and now the third line of defense, the actual quality assurance process. So you've labeled your data. What happens next? It's the QA process. So again, having that continuous feedback, iterating quickly with what the labelers are actually doing, implementing that continuous dialogue between the labeler and the reviewer, and understanding what each person is doing. You can also implement random sampling or targeted review based on certain conditions. So generally you want to start with random sampling, and then you might be guided to oh, we're consistently getting this type of error, which you might then want to spot check in a targeted manner in the future. And there are various ways of doing that, which can involve metrics, which is my last column here. So understanding the consensus between labelers. So if you have two different labelers label the same piece of information, they will not ever 100% agree unless the task is very, very clear. I've very rarely seen 100% consensus on a project level, certainly. So you can compare, of course, with model results in two separate ways. You can have both the model confidence score, of course, that might be passed back to you from a machine learning engineer, but then you can also make inferences on top of labeled data and compare the inference to the actual labels generated by humans. And what that can do is give you, again, a consensus with the model, understand, okay, is it my humans are wrong or is my model wrong? And give you an understanding for that. Okay. I have a short demo here, so I can bring that up here. So this is the Kili platform. I have a sentiment analysis demo going on here. I can see that I have a bunch of different assets in here with different statuses, different consensus marks here, that's here. And then I can go into this explore mode here, and I can actually see my data and the task at hand. So the task here is to classify the entire entry as one of these classes over here on the right, and then label the text that fits that class that was selected. So these are job reviews scraped from Glassdoor, and you can see that you know, there's some enthusiasm here in this particular asset. One thing that's great about this platform for Kili is the ability to filter down quickly to exactly what you want to be seeing. So maybe I'm interested in only things that were labeled on a certain date. I can, of course, do that. Or only labeled by a specific person, maybe only me and Jean. And then maybe I'm only interested in label classes that have these two classes in them. So I can stack these classes, these filters up. I can then sort by external ID. I could sort by consensus in this list and understand, okay, where exactly are we disagreeing, Jean and me? And then I can drill down to a asset level view and understand, okay, what exactly is the difference between these? And that is an example of how you can use the Explore page in Kili to add filters and narrow down your QA analysis. All right, we'll go back to presentation. All right, so what does this mean for your overall project lifecycle? So generally, it can be split into three different sections. One is like the first batch of data that you get. You're really just experimenting a lot here. You have your first draft of your project design. You have an idea of what you might want to be doing with it, tied to some business value. You might be onboarding your labeling team at this point, and you'll really be doing a lot of QA in this. A lot of a lot of effort, a lot of time expended to get it right, which is exactly what you want to do because the amount of data is small. And then you'd move on to iterating around. You'd understand kind of your main cases within your project design. You'd be training your labeling team. You might have a medium amount of QA process, still, again, iterating some. And then finally, when you're scaling up, doing a ton more data, going from 100 assets to 100,000 assets, you really want to make sure you've got everything designed right, which is why you spent so much effort in the first couple of steps. You have, a great project design. You have all of your edge cases identified, hopefully, or at least many of them. You have a fully trained labeling team that can share tasks between one another, and your QA processes are generally a low amount of the data, 20% or less. So you're really doing spot checking or random sampling for very specific errors that you might encounter. I have one use case here that we implemented with JellySmack. They are a video annotation company. Well, they use video annotations to do a lot of their ML work. And what they saw with implementing Kili was they saw a 10% increase in the accuracy of categorizing their videos. It's a big use case for them. They saw a huge increase in the productivity of their labeling teams and data science teams, and they saw a lot less demonetized videos. So that is their main use cases. They reformat videos to post on a bunch of different channels across the internet, which have to comply with all sorts of different standards for how you post them, what can they contain, et cetera, et cetera. So their goal is to have a high monetization rate and a low demonetization rate for their videos. So that is a huge improvement for them. And then a 2 to 10 time factor of reduction in the actual training phase of a model because their data was so much better. They didn't have to have as much of it. And they really got a lot of benefits from implementing these types of systems. Okay, some key takeaways. Here I have 3 for you. Again, in project design, labeling team and QA process. So for project design, labeling your own data, understanding and investing time in guidelines and ontology can make them really live during the project so they can have a life of their own. Again, iteration is a theme of this presentation, I guess. So being able to iterate closely with the labeling team and building interface safeguards into the platform itself can be hugely beneficial. And then finally, for QA processes, ensuring that you're actually manually reviewing some of your data. It is sometimes maybe viewed as a pain to do, but it is still an important step. And then you can always leverage the metrics to target that review. So it can still be manual. A lot of people want to just automate everything, bring in a model, it's going to be fine. But there's a lot of nuance in this type of data, unstructured data, that you might miss if you don't actually look at it yourself. So again, leverage those metrics to target the review that you are doing, but still do it.